Long time no see, everyone. Finally back. Hope assignment 3, handing in all that stuff went well. Now we're on to assignment 4, and we're going to spend the first little bit of class just going over that. And then we'll finish up the content for this week. The fact that I had to cancel class last time might have been a good thing, because then we're closer to being on schedule. Still a bit ahead, though. Anywho, this assignment overall is based on one kind of overarching task, except for the proof bit. That's completely separate. And that is to implement binary tree traversals iteratively. We talked a bit about traversals in class, specifically the depth-first traversal, which goes all the way down a given branch of the tree before continuing. So we know about that. We saw a very easy recursive algorithm to do that. I've memorized it. It's something like depth-first search the left side, print out the current node, depth first search the right side. It's easy. Doing it iteratively, though, is a bit trickier and requires the use of a specific data structure. I'm not going to tell you which one, but I hope it's pretty straightforward to figure it out. And then breadth first search is totally new. I'll talk about it in a few minutes, but it, as far as I know, has no recursive algorithm. You have to do it iteratively and using a specific data structure. Also, zooming out a bit, just some first year review. Iterative algorithms are generally better than recursive algorithms because calling functions has some overhead. It's not the kind of thing that shows up in asymptotic notation, but practically, if you time execution time, if something like a while loop will go faster than a recursive call. I think this first page is mostly copy-pasted from the previous assignment, but I want to point out that some of the requirements are a bit more strict. Last time I was fine with y'all using linked list, like the built-in Java linked list class, in order to implement separate chaining, because that part wasn't really about linked lists. It just happened to use linked lists. This is kind of the same. A stack or a queue implemented using a linked list happens to use it but isn't about it. But Java's linked list class is super fancy and includes all the methods you would need to implement a stack or a queue. So I want your stack and queue methods to be 5 lines long, not 1 line. So using that isn't allowed. Also, I use this phrasing or any other such classes to prevent cases where you guys outsmart me and think of a class to use that I haven't thought of. But still, if you do, and you think that it might be, you think that a class that you found that's built into Java might be useful for the assignment, but won't ruin the educational value of it, let me know. I'll gladly make exceptions for things that just make life easier while still making this a learning experience. So, iterative traversals. Lots of preliminaries for this one. The first 2 questions, 3 if you count question 0, are all preliminary work. There's a zip file on UMLearn that contains a bunch of files that you could use to get started on the assignment. Your stack and queue are going to use this class node The node class is made for use in a binary tree. In isolation, it's kind of stupid to make the stack and queue class use this node class, but it makes sense in context because in your iteration algorithms, your traversal algorithms, your stack and queue will be storing node objects. This should be everything that you need. It's got getters and setters for all the properties you'd expect it to have. But if you need to add to it, you can. The markers won't be replacing the file with their version or anything like that. For the next few questions, there are skeletons of the classes that you need to implement. Here's the one for stack, for example. It'll compile, but it won't do anything. It's your job to fill in the methods. And the reason I gave you guys these bits of code, besides making your life slightly easier because everything is hard, it's because the markers will be testing your code using code that you haven't seen, will not ever see, although I'll probably show it off when I'm going over the solution. Their code depends on things like the stack having a pop method that returns a node and takes 0 parameters. So you need to keep this interface the same, or else the marker will see that your code crashes and you'll lose a bunch of marks. Of course, if you want to add private methods to make implementing these public ones easier, or even new public methods to make communication between classes easier, go for it. Just don't modify any of the function signatures. Another important note is that you'll be expected to test your own ADTs this time. You are welcome and even encouraged to use my tests for the inventory from the last assignment as a starting place. The tests that the markers are going to use also use that assert, try, catch, print an error message sort of structure, but you can too. I'll happily talk about testing more in class if there are questions, but I hope this is relatively intuitive. You have a pretty clearly defined interface for your stack, and your tests need to make sure that all of these methods work. And there should also be some variety in your tests using both typical cases and edge cases. A typical case would be just how you expect the class to be used. For a stack, a typical case would be pushing 10 items and then popping them and making sure they're in the right order. An edge case is an input that's weird but still valid. So trying to pop from an empty stack is an edge case. So your test should make sure that it returns null and doesn't crash in this case. Oh, and you can choose which data structure you want to use when implementing the data structures. The question of which one to use isn't really deep here, so I recommend making a decision based on which is easier to use. Oh, scrolling's all janky this morning. Then you'll build and test a binary search tree. This assignment will start to feel very formulaic until it all comes together. And you'll make methods for iteratively traversing the tree. So a depth first search does a pre-order traversal. We learned about that in class. And then the breadth-first search is the new, wait, I might have named this traversal in the code. If I did, you should trust the code and not the assignment, but I'll update the assignment. Yeah. Okay, pretend this says traversal instead of search. I'll update this later today. A breadth-first traversal is a traversal that goes level by level rather than going all the way down the tree before going back up. So you could see here it starts at the root, goes to all the nodes at level 1, goes to all nodes at level 2, all nodes at level 3, and all nodes at level 4. Cool. As an aside, breadth-first traversal is used a lot in AI and machine learning. Oftentimes, the decisions that an algorithm, or a model, I guess, the decisions it can make can be modeled as a graph, and said graph might be infinitely large. So if it does a depth-first search, it might go all the way down one path in the graph and then never recover, never find a good decision to make. Whereas a breadth-first search I don't know enough AI and machine learning stuff to explain this well. It avoids getting stuck. That's the best explanation you'll get for now. No recursion allowed, write tests. You got this. And finally, there's a proof question. This one is kind of cool, but we might disagree on what cool means. This is all stuff you've seen before. You won't really have to wrap your head around any new techniques to do this, but it uses a lot of the techniques we've learned throughout the course, and it won't be immediately obvious when to use each thing. So I gave you a hint on how the proof might be structured. Show that the height is logarithmic when the tree has a minimum amount of nodes, and that it's also logarithmic when the tree has a maximum number of nodes. And you have a few facts that you can use. But other than that, you're on your own. Like I said, the techniques used are all stuff you've used before, but it'll take some creativity to figure out when and how to use them. So that's all for assignment 4. I'll stand here for 15 seconds or so. You can ask any questions. But after that, we'll finish up this week's content. Yeah?
Okay, so if limits are just confused, why do we even bother with this stuff?
Well,
Because it's good to know the formal definition of these things. Limits are actually kind of informal. You learn how limits really work in a second or third year calculus course. But if we're focusing on rigor at this level, we're not going to use the formal definition of a limit. So the best we could do is continue to use the formal definition of the asymptotic notation.
So what's used more commonly in industry?
The method where you look at the code, go that's a loop. That's O of n probably. I fully admit this is not an industry thing in this question. This course looks at both practical matters about how these things are used in the real world, and more theoretical stuff, how it really works, stuff that's less of interest to businesses and more of interest to academics. You're here to learn both of these things, and this is much more of an academic thing. Any other questions? Yeah. Sorry, I'm having trouble hearing you. Did you say you're asking about the first question?
Can you provide a pseudocode for the first traversal?
Oh, okay. No, it's I recommend trying out the depth first traversal first, based on what you know about the recursive version, and then breadth first traversal will actually end up working very similarly to the depth first traversal. You could also try to do your own research online. There definitely is pseudocode that exists, but take caution because the pseudocode that you would find on Wikipedia, looked it up, is for general graphs, not trees. And breadth first traversal for trees works a bit differently from breadth first traversal to graphs. Yeah. So in summary, I won't directly find the pseudocode, but you can research online and also start from something more familiar. Anything else? All right, let's get back to this week. We ended our discussions last week by talking about the delete operation for 2-3 trees. Sort of like the delete operation for binary trees, the delete operation for 2-3 trees had a few different cases. Excuse me. In general, the algorithm is that if you're deleting a leaf node, delete it directly. If you're deleting an interior node, then swap it with a leaf node, and then do the deletion from there. Or swap it with its immediate successor specifically, not just any leaf node. We looked through the first couple cases on Friday, but then I left off on a cliffhanger. We'd have to find out how the hardest case works later. I'm just going to quickly go over the relatively easy cases and then spend more time on the tricky case. So if you're deleting a value from a leaf node, this is easy. And actually, I should correct myself. I've been using terminology like deleting a node, but it would be better to say deleting a value from the tree, because in a 2-3 tree, nodes can have multiple values. In this example, we're deleting 19, not the node that contains 19, because 21 still has to stay in the tree. Anyway, the easiest case is if the leaf node contains the value you're deleting and another value. In that case, you just remove the value. It's that simple. No need to rearrange anything. This case is a bit trickier. If you're deleting a leaf that doesn't contain any other values, it'll leave a gap. So you have to rearrange some of the values, essentially taking a value from the parent and then promoting a value from the sibling to become the new parent. So in this case, delete 21. Yeah, you delete 21 and then move its parent value into the node, which leaves the parent empty. And then you move the larger of the two values of the sibling to the parent. This procedure makes it so all of the necessary properties of a 2-3 tree are preserved. You still have the search property where all the nodes on the right of a given node are larger and all the nodes on the left of a given node are smaller. And also you keep the definition, like the recursive definition of a 2-3 tree, which I'm going to let us get sidetracked to because it's totally a hint for the assignment. Come on, scroll bar. Yeah. All right. This isn't that relevant for the delete operation, but I'm pointing it out because you'll need to refer to this pretty directly when doing that proof at the end of this assignment. So we have earlier defined a 2-3 tree as either a single node or a root node with two children, each of which is the root of a 2-3 tree of height h minus 1, where the tree overall had height h greater than 0, or a root node with three children, and three children, each of which is also the root of a 2-3 tree of height h minus 1. So that delete operation prevented a case where a node had, say, two children, and actually this wasn't included in the definition, but sort of follows something like two children and two values in the root wouldn't be allowed. The delete operation prevents that. And now I want to actually continue getting sidetracked because the definition that I wanted to point out didn't have all the stuff that I wanted to point out. The thing that'll be useful for the assignment is the fact that a node has 0 or 2 children if it has one value, and that it has 0 or 3 children if it has two values. So keeping this in mind, you can probably figure out what the minimum and maximum number of nodes in a 2-3 tree of a specific height is. But I'm not going to spell it out. So let's get back to deleting stuff. So we did the easiest case, we did the trickier case. And here's another example of the trickiest. Yeah?
On that previous example, that node that had 13 and 15 had two children called, I guess, 12 and 16. So this would be defined.
Wait,
Yeah.
right
If
here.
12 and 16, then you would, I guess you would take 16 and put it up there, and then you'd have a 12 and 13 node.
Are you saying if this node had more children?
Yeah.
Okay. So something like this?
Yeah.
Okay, so a situation like this actually is prevented by the definition. the definition forces the 2-3 tree to be perfectly balanced, and this tree isn't balanced because one of the subtrees, in this case the one rooted at 13 and 15, has a greater height than the others. Moreover, since this node has 2 children, it would have to have, this node has 2 values, so it would have to have 3 children. So a situation like this, I actually don't have to give a good answer for because our algorithms ensure that it would never happen. Right, so if we delete a 1, we're going to pull down a value from the parent and bring up a value from the sibling. Okay, let's get to the good stuff. We're going to delete 5 from the tree. And the strategies we've used thus far won't work anymore because there are no siblings to get values from. So delete the 5, and then what happens? You're going to merge the empty node with an adjacent sibling and then pull down a value from the parent node. So in this case, we had 3 children under the node containing 4 and 8 before. In previous cases, we would have kept the number of nodes. Notice how deleting 1 in this example resulted in that parent node still having the same amount of children as before. But in this case, we actually just let that node die. We end up with 2 children. And this actually goes back to that case that you were asking about, because we now have a configuration where a node has 2 children and 2 values, a configuration that I had earlier said was impossible. So before the delete operation is over, we need to resolve this and turn this branch of the tree back into a configuration that's allowed by the definition. So this node has to either contain 2 values and 3 children, or 1 value and 2 children. Or if we do some like radical rebalancing, it could have any number of values and 0 children, but that's not going to happen. What is going to happen is pulling down a value from the parent. The parent node now has 1 value, as it should, given that it is an interior node with 2 children. And now this leaf node is it has 2 values and 0 children, which is allowed because it's a leaf. So that was the trickiest case, but it might not have seemed that trickiest yet.
Why did I pull out the 4 and not the 8? And I don't mean stick the 8 with the 2, I mean stick the 8 with the 10.
Oh, wait. So you're wondering why we do this moving down the 4 instead of that moving down the 8?
Yes.
Okay. I'll have to think about that for a moment, but I think that what you're suggesting would still work, and that the reason why we do one or the other is just because we had to pick one. But let's see. Yeah, I see nothing wrong with this. The definition stuff is still preserved. This node has one value and two children. The leaf nodes can do whatever. And the search property is preserved, where all the nodes here are greater than the node here. So, yeah. It's like how we talked about deleting from binary trees last week, and I mentioned that there were multiple algorithms for deleting from a binary tree, but we're only going to cover one in this course. The delete operation I'm going over here is not the only way to do things. Right, anyway, that was the trickiest case, but might not have seemed so tricky. The real hassle of this operation is the fact that it might have to be repeated, might have to get kind of recursive, kind of. We're going to delete 18. There are no sibling values we can borrow from, so we look to the parent instead. But the parent only has one value. If we move the parent down, we'll be in the exact same predicament as last time. So we're going to have to end up moving a value down from one of its parents, maybe, but that would result in a node with, don't copy this, this is bad. That would result in a node with one value and three children, which is also bad. So what we're going to actually end up doing is applying that merge idea once again. We're going to merge this now empty node with one of its children, end up with the root having two child nodes, and then pull down a value from it. I'm going to stop trying to describe it in words. Pictures are way easier. So you delete the 18. It's empty. You merge the empty node with an adjacent sibling. Diagrammatically, this is kind of weird. It doesn't really feel like we're merging anything. We're just drawing the diagram again, but excluding this node. But if you're programming something like this, then the merge operation might make a bit more sense. You might be changing references so that two formerly unique pointers point to the same object. Anyway, pull down a value from the parent, which, as I talked about before, leaves us with another empty node for us to deal with the exact same problem. So we're going to recursively apply the delete procedure to the parent node. If one of its siblings had two values, we would go back to the slightly easier but still kind of tricky case before. Like, I don't know, if this had it would be not straightforward enough for me to just figure it out live, because if there was like another value here, we wouldn't be able to redistribute it directly, because that would mess up the search property and result in a node with one value, one child, which isn't allowed. But I'm sure either of us could figure it out by just sitting down for a while with the earlier slides. Also wanted to mention, we can't just move this node up, and end up with a configuration like this, because, again, violates the definition. But in slightly more practical terms, that would cause the tree to become unbalanced because there's a root, or there's a path from the root to a branch there's a path from the root to a leaf that is shorter than others. And the whole goal here is to make it so the path from any leaf, or from the root to any leaf, is the same length. So we get that awesome O of log n search complexity. Anyway, we do that weird not quite merging thing with a sibling. We go to the left sibling, but the right sibling would probably work too. And now we have a configuration that's still illegal, but not unjustified. It's closer to being something conformant with the definition. And also, the naming of this operation as merge makes more sense here because the things that we're merging both have children. And in the end, the merged node has all the children of both of the nodes we're merging. Anyway, try to guess what's going to happen next. There's only one more thing we need to do to make this evil monstrosity into a valid 2-3 tree. We're going to pull down a value. In this case, it gets the node that we're operating on gets the middle of the two, no, it gets the lesser of the two values from its parent. If we had moved it to its right sibling, it would get the greater of the two values, all in the name of preserving the search property. But now it's all good. Every node is either, every node has either one value and two children, three values. Ugh, this is so confusing. Every node has one value and either 0 or 2 children, or it has 2 values and 0 or 3 children. It's a good tree. The process stops when there are no empty nodes left. Might even rephrase that to say that the process stops when no illegally configured nodes remain. That's not as catchy. What I'm trying to express here is that the process isn't over yet when we have something like this. Yeah?
So, you know how you pulled down 11 to 8?
Mm-hmm.
Could you pull 13 up into that node instead?
Ooh. Yeah. Similar to a previous question, I don't see anything wrong with this configuration. I would be a bit weary, though, about being able to make guarantees that it's possible to do that pull. In here, it's always possible to pull one of the two values from the parent because we start with 3 children, and thus the parent would always start with 2 values. But the definition of a 2-3 tree makes no such guarantees about whether any of its children will have 1 value or 2 values. So, it's definitely possible that your idea would work in general, but I'm not sure. I would have to think about it a bit more to give a definitive answer. that's all for 2-3 trees. I think there's enough. Oh, yeah?
So when we did that merge thing, what if we wanted it to keep two at the top and we wanted three for that second one?
Ooh. So, like, what if you wanted the root node to stay how it looks right now and still have 3 children?
Yeah, like I don't know, like if we took 25, stuck it up to the top, pushed 22 down, stuck it on the right side of the third level, and then stuck 15 where that red dot is, and then we could just rearrange the right side to like.
Yeah. Okay, now I think your thing is similar to the question that was asked previously at this point, because everything you're saying would work for this specific tree, but I'm not convinced that it would work in general, just because I feel like that requires a bit too much human thought. Looking at the picture and moving things around. The thought processes we're talking about right now would be pretty hard to translate into code. There absolutely are different ways to turn this into a valid tree, but the one I'm describing because it would be feasible to make this into an algorithm. Yours probably is too, but I'm not immediately sure how you would do that. Right, last thing I wanted to mention before getting a preview on next week's material is that the quiz for this week, pretty simple concept. I'm going to take last week's quiz and replace the binary trees with 2-3 trees. That's it. The deletion bits won't be too complicated. I think it'll be like at most as difficult as the example I just did, probably a bit easier. But to be safe, make sure that you understand the examples in all of these slides. Well, we're on to week 10 already. Isn't that crazy? We're going to be continuing to talk about trees for the next little while. And like from a more high-level perspective, we're going to be talking about nodes or data structures that consist of nodes and edges between them for the rest of the course. Our next topic is going to be AVL trees, which are a different approach to maintaining a balanced binary search tree. So we're familiar with the problem with binary search trees. If you do everything right, they'll be nice and balanced. There will be a short path from the root to any of the leaves, and searches will be fast. But they can degenerate into what's basically just a linked list. And then the worst case for doing any of the operations involves going through every single value of the tree rather than logarithmically many of them. 2-3 trees solve this problem by changing what a node can contain and imposing pretty specific rules on what children the nodes can have. An AVL tree, on the other hand, is another solution to that same problem. It keeps the structure of a binary search tree where every node has one value and 2 children, but it has some pretty neat, just fiddling with stuff on this other screen so I could get these slides up. But it has some new rules and new weird special cases in its operations to just take the existing idea of a binary search tree and make it so it stays relatively balanced. We're not actually going to have the perfect balance of a 2-3 tree. In a 2-3 tree, all paths from the root to a leaf are the same length, but an AVL tree won't make that guarantee. Instead, we're going to basically guarantee that the tree is balanced enough. If the left and right subtrees of a node have different heights, they're not going to be too different. Oh, and the AVL tree was named after its creator's initials, A, V, and L. How much should I do here? Yeah, I'm going to try and go up to balancing factor. So the height of a node is a number of edges on the longest path from it to a leaf. And an empty tree is defined as having height -1. So this is a generalization of the idea of the height of a tree. So this entire tree has height 4, but its subtrees also have heights because they are also trees. So this subtree has height 2 because the longest path from root to leaf has 1, 2 edges. A node with 2 children or nodes with 0 children have height 0 because the root of this subtree is also its own leaf. There are no edges in between. And completely empty trees, the lack of a subtree, has height -1, which doesn't really have a good intuitive explanation, but the fact that we've defined it this way just fits in really well with the math that we'll be doing. The balancing factor of a node is the difference between the height of its right subtree and the height of its left subtree. The whole big idea of an AVL tree is that the balancing factor of every node in the tree has to be either -1, 0, or 1. So the heights of its 2 subtrees differ by at most 1. So, at a glance, I think this tree is a valid AVL tree. I'd be actually very happy if someone put their hand up and proved me wrong. But it seems that between any pair of siblings in the tree, their heights differ by at most 1. This subtree has height 3, and this subtree has height 2. That's okay. The definition of an AVL tree considers this to be balanced enough. Oh, wait. Aha, -1 minus 1 is -2. So yeah, this isn't actually an AVL tree because the subtree rooted at 14 has a left subtree that's just too tall compared to its non-existent right subtree. So this is bad. And it would need to be rebalanced somehow. How exactly are we going to do that? You'll find out on Friday. That's all for today. Good luck on the quiz.